So our next speaker is Tomas Stachowiak, who is a rendering engineer in the Frostbite engine team at Electronic Arts. He specializes in physically based rendering and is passionate about lighting, climbing the Akali Valley, and obsessing over the tiniest details. He's previously worked at Creative Assembly, where he would spend his time polishing xenomorphs for alien isolation.
Thanks, Natasha. Hi, everyone. I'm Tom. I'm a Polish pixel polisher at Frostbite. I would like to show you some of our latest shiny. This is work which has been done in collaboration with Yasin Uludag from the DICE team. We're going to start by showing you some pictures, the kind of which inspired our work on SSR. And then we're going to go through a few algorithms which have been done in the industry. Then finally, we're going to go to our algorithm and reveal some of the secret sauce which makes it practical and pretty. So without any further ado, so here's some pictures. The first one is a concept art from the upcoming DICE game, Mirror's Edge Catalyst. And as you can see, pretty much everything in this shot is reflective, and not all of those reflections are fully mirror-like. You can see some glossiness on the right side. On the left side, there's some like an anisotropic shape in the reflection. And the next one is a photograph of one of our conference rooms. And as here, there's something quite interesting going on. You don't quite see reflections per se, and instead what you have is the occlusion of reflection of the outdoor light. And this is actually highlights a key feature of SSR, which is quite often underplayed, is that it allows you to ground the objects and to have occlusion between them. It also has plenty of rougher surfaces and some variation in the glossiness. And you can see contact hardening in the reflections just next to the chair legs, for example. And this is something which you might see, for example, in the racing game. And a few interesting effects as well. So you have the stretching of the reflections in the vertical direction, which is quite an important visual effect. And there's also variation in the roughness and normal maps per pixel. So with those, we can actually formulate the list of requirements for our algorithm. So for starters, we would like to support sharp reflections, but we would then like them to also get blurry. But this isn't exactly what we would like to have, because reflections should harden as they go close to the surface which is reflecting them. And next step, we would like the reflections to stretch vertically. This is something that you probably already have if you're using microfaceted BRDFs with analytical lights, but we would like our reflection techniques to support this as well. And finally, we would like them to support per pixel roughness and per pixel normal variation without artifacts. So let's see what kind of previous work was done to handle SSR. And there was plenty more than I can cover here, but this is going to be just a few which inspired our work. So the first one is just a basic version of SSR you can implement. So you start with a depth buffer, with a G buffer, which contains depth and normals. And this allows you to define the mirror-like reflection rays for each pixel. And the limitation of this approach is that it will only support mirror-like reflections. So with the generated rays, you pretty much just ray march through the depth buffer using any kind of approach, for example, with constant size stepping in screen space. Then at the hit point, you have to sample and return the color. You can either use some information from the current frame, or more commonly, actually, you can reproject the previous frame. And this way, you can actually also get an approximation of multiple bounces in the reflection. So this works with normals just naturally, but doesn't give you glossy reflections. There's a way to fix that. For example, the approach implemented in Killzone Shadowfall. So they generate an image with just mirror-like reflections. And then what they do is they convolve the result using successively wider Gaussian blurs. So they create a mid-pyramid. And then with this mid-pyramid, you can actually select the level of blurriness for each pixel and get the per pixel roughness variation. But what this doesn't do is keep the normals, because the filter is not feature aware. It's actually going to kill the normals on the rougher reflections. And it also doesn't give you contact hardening, because again, the filter doesn't know about the distances to the objects. So it is going to just blur out from through the contacts, and you get those kind of reflections. There's a technique which actually fulfills all the requirements and gives you the contact hardening, the stretching, the glossiness, and so on. And it's important sampling, and this with or without the filtering. So the way this works is you trace several rays per pixel. The rays are defined by the local surface properties, or the BRDF. So for example, when you have rougher surface, you're going to have rays which are dispersed. And when you have a smoother surface, they're going to be more coherent. And you take samples from a color buffer, which can be pre-filtered, and then you just integrate them. And with enough samples, you're going to have a smooth picture which has all the features. But the problem is the keyword, enough samples. It's actually very difficult to do it in real time because you're going to have plenty of noise in the picture. Our approach actually uses importance sampling as well, but we also take the idea from Killzone by doing filtering in image space, although our filter is quite different. So what we do is we importance sample first, but using only very few rays per pixel, for example, just one. And the key difference is that we don't return the color immediately. What we do is we actually store the intersection points in the first pass. And then we have another pass which is able to reuse those intersection points across local neighborhoods. So we basically pretend that the rays trace for neighboring pixels or trace for the given pixels we're trying to resolve. And this allows us to multiply the number of samples without actually tracing any more rays. Now, and another thing which we do is taken from the filtered importance sampling approach is we take filtered samples and not just sharp ones, and we calculate the filter size based on the distance to the reflecting object, so we don't kill the contact hardening. We also are very careful with the weighting of each contribution, making sure that it matches the local BRDF of each pixel, so we don't have blurriness in the result. Here's a few screenshots. This is just a simple case where you have a mirror-like surface, just to show that it works. And then a more glossy one, which clearly demonstrates the importance of the contact hardening. And here with some normals as well. And some smoothness variation. And here's a scene which has quite some material variation and pretty complex visibility in a few places. And this is without SSR. And when they enable it, you get a very nice glossy reflection of the car on the floor. And if you look at the rims before and after, it also gives you this kind of very nice shadowing reflection. And this one is a screenshot from Mirror's Edge Catalyst without any reflections at all. And now with SSR enabled and SSR plus fallback to IBLs. And this is just the SSR. So you can see that the normal detail is preserved. You get the contact hardening. You get the glossy reflection. It's actually a pretty difficult case for the system. So hopefully that you like the results. We can go through the algorithm. We begin with tile-based classification. So we subdivide the screen into tiles, and then for each tile, we decide whether it needs SSR at all and just how much work we need to spend calculating it. Then we allocate arrays and perform importance sampling on them. Once we have the arrays, we perform ray tracing in two flavors, actually. And afterwards, when we have the intersection points, we perform a color resolve pass, which does the ray reuse. And once we have the color, we perform temporal filtering on it. So as I mentioned, we begin with tile-based classification. So at this stage, we actually already performed some ray tracing. So at a very much reduced resolution, we should rate some rays and just decide for each tile whether it is going to need SSR at all. So for example, you could be looking at a reflecting wall straight up, and all the rays will be going towards the camera. So for those, we actually don't need to calculate anything, and we can skip some work. And we also sample the color buffer here, and we do an estimate of the perceptual variance we're going to have. So if we're hitting a high contrast surface, we will decide to allocate more rays for the pixels in this tile. We allow the content creators to specify a min and max value for the rays for each pixel, and based on just the contrast, we decide if it is likely to be noisy and to allocate more rays for it. So now that we know how many rays to trace, we also classify them per pixel. So for each pixel, we take a look at its roughness, and for the mirror-like reflections, we actually want the reflections to be as exact as possible to avoid artifacts. And for those, we have a high-precision hierarchical tracer. Whereas if the reflection is going to be blurry, then we don't need the exact intersection points because the result is going to be blurry and filtered anyway. So for those, we have a linear marcher similar to the one described by Morgan McGuire. As for the hierarchical tracer, I'm not going to go into too many details of it, but it's actually quite simple. It's basically a stackless traversal of a quad tree. And this was described by Yassine in his GPU Pro 5 article and a few publications online. So the idea is that we start at the most refined level, and then whichever cell of the quad tree we are in at a given moment, we try to trace the ray towards its edge or the depth plane. So if we don't hit the depth plane, we just carry on. And if we didn't hit the depth plane, we also increase the level of the quad tree, so go to a coarser level. And this allows us pretty efficient empty space skipping in the tracer. But if we do intersect the depth plane, like here, we actually go to a more refined level again. And we repeat the process, and once we find an intersection at the most refined level, we know we have a hit point. So that's basically it. Now I have mentioned that we use importance sampling, but you may not be intrinsically familiar with the concept. So it is a variance reduction technique for Monte Carlo integration. So suppose we have a function we would like to integrate. What we need to have is a probability distribution function, which is as similar as possible to the original function, and one which you can sample from. So we generate samples from this function, for example, using the inversion method. Then for each of the samples, we evaluate the value of the original function, and we divide by the value of the probability distribution. And if we average a number of those samples and the sample count tends towards infinity, we get closer and closer to the target integrand. So we use this technique to generate samples from the BRDF at each pixel. And any BRDF can be used with the technique, actually, but we happen to use and worship GGX. And we cannot use just about any lousy samples. We would like them to be of high quality because the ray tracing is expensive. So by making sure that our samples are of high quality, you can reduce the noise quite considerably. So as a very bare minimum, we use a low discrepancy Halton sequence to generate them instead of just uniform samples. But even with this, using the classical importance sampling approach, we can actually end up with rays which will be going below the surface. There are many ways which we can handle that. What we do is actually we just detect those and we regenerate them. Now this is actually an area of future work for us because we're planning to use the distribution of visible normals from Eric heights, which would mean that we wouldn't be generating those rays in the first place, but this scheme actually works well in practice and doesn't increase the timing in any considerable way. Now once we have generated and traced all the rays and we have the intersection points, we perform the color resolve class which does the ray reuse. So the idea is that local proximity in screen space also means proximity in word space, and we just assume that the visibility between the local neighborhood and the hit points is going to be similar. It's not always the case, but in practice it actually very often is, and the BRDF weighting we do afterwards ensures that the artifacts are minimal. And this is actually the same assumptions that any filters which perform blurring in screen space will have as well. So we pretty much just transplant the intersection points across the local neighborhood, and we connect the rays to them. Now, we still have to be careful with this because that integrand we need to have it correct as well. So we, as shown before, we have to multiply the results by the BRDF function and divide by the value of the PDF. But we have to use the PDF of the neighboring pixels that the ray was traced with, which means that we actually return this from the ray trace function itself. Now, we have been slightly optimistic with this and assuming that the neighborhood's PDF is going to be a good match for a local function, but this is not always the case. And then we can have spikes in the BRDF to PDF ratio, which will result in noise. And here's an example scene with some variation in the roughness normal. And here's the result of ray tracing with just one ray and one resolve sample at half resolution without any filtering. And now if we actually do the reuse, we can get results which are more speckly than the original. Some of the surfaces are slightly smoother, but in general, you have this speckle which is difficult to remove afterwards. In order to fix this, we actually have to take a step back and look at what we're trying to solve here. So this is the scattering equation with the emissive light term removed for clarity. So we have the incident radiance, we have the BRDF, and the cosine term. And this is the same thing expressed using Monte Carlo integration with importance sampling. So this is the term I mentioned which creates the variance. We would like to eliminate it. So what we do is we multiply and divide the original integrand by the same value. And this value is just the integrand of the BRDF and the cosine term. Then what we do is we pre-integrate this term. And if you're using image-based lighting with physically based rendering, you probably are already calculating this term, because this is the same thing which allows you to get proper Fresnel and geometric masking with IBLs. This is the same term that Brian Carris described in his 2013 course, talking in the physically based shading course. So we basically just handle the rest using Monte Carlo integration. And does the same thing with some annotations. So at the top you have the BRDF weighted, and BRDF and cosine term, I guess, weighted image contributions. And at the bottom you have just the BRDF weights. So effectively this works as a renormalization of the BRDF weights, which allows us to eliminate the resulting spikes, which would just, if this integrates to a value which is not 1, we actually force it to be 1, and then multiply by the pre-integrated value that this should have. And in code this ends up being super simple, because this is basically just a weighted sum. So here's the same screenshot with just one ray and one resolve sample per pixel without the normalization, and again, no normalization, and now with a new trick. So you can see it pretty much just removes the artifacts. And here, instead of using 4 resolve samples, so 1 for the local pixel and 3 neighbors, we actually are shooting 4 rays per pixel and not doing any resolve. So you can see that the variance is actually quite similar. So we get away without actually tracing, and we get similar variance reduction in screen space. And here again with just one ray and no reuse. And here with 4 rays reused. So you can see this actually reduces variance quite nicely. And we can mix and match, so we can trace more rays per pixel and then use the resolve samples. So here we trace 4 rays and we use 4 resolve samples, which results in 16 color values being evaluated per pixel. So this is starting to look nice, but it looks like we're going to need lots and lots of samples to make this smooth. So we use everyone's favorite technique these days, which is temporal filtering, which produces even less noise. And the weight renormalization actually allows us to do one more trick. When you use the neighborhood, you actually will usually find some rays which are useful for the given pixel, and that holds true even if you don't have any rays for the local pixel. So we don't need to trace rays for other pixels. What we do is we actually ray trace at half resolution and then just use the resolve pass at full resolution. And we get the full resolution details from the BRDF and all the weighting and so on. So again, this is just half resolution. And this is traced at half resolution but resolved to full res. And as you can see, the noise is actually lower as well, and that's because our temporal filter is tuned for the full resolution pictures. And now the key part of the temporal reprojection is the depth value. So if you try to do reprojection in a naive way, like you might do for ambient occlusion, you will notice that the reflection is actually smear. Like on the left, you can see them being quite ugly. This is because reflections have different parallax than the values, than the surfaces they are reflecting in. So what we do is we actually extend the depth using the length of the full ray from the camera through the reflecting surface to the reflection surface to the reflecting surface, and that eliminates a lot of the smearing. Now this is something shameful, which I have to admit, is that we don't use pure unbiased Monte Carlo, because that is still very difficult to resolve the noise with. And you get plenty of variance, especially from the tail of the BRDF, which produces chaotic rays. So we actually bias them towards the mirror direction. But this cannot be done naively, so we actually have to still be careful with the PDF values we calculate. So we use truncated distribution sampling. So we just cut off a part of the BRDF. And then we reallocate the rest, the lost weight, into the front area. This results in different normalization constant, but since we have a renormalization pass in the resolve, we actually don't even need to calculate it. So this ends up being a super simple thing. And then I mentioned importance sampling, but there's also the filtering part of it. So we start with a pre-filtered image perimeter, which is actually the same thing which we calculate for bloom and post-processing. And we then, when we trace the rays, we pretend there are cones on the intersections. we calculate the extent of the cones, and from that we can find the MIP level to sample for each ray. So this can actually be biased as well. We can tune it to produce blurrier images than what we would like, and we actually use that as a feature to counter the bias we get from importance sampling. The bias in importance sampling makes the picture sharper, but this one makes it blurrier. So we actually wire the two parameters together, so at the value of 0 you have pure unbiased Monte Carlo, and at the value of 1 you're always tracing in the mirror direction and just taking the blurriness from the filter. And this actually improves performance on two fronts. Because the rays will be more coherent, we actually get more coherent memory accesses, and because the filter will fetch from higher MIPS or lower resolution images, this will actually also reduce the memory bandwidth. So here's an image with a bias of 0, and here it is with bias of 0.7. As you can see, the overall look of the image is preserved. Some of the elongation will be lost in this, but the performance is better and the noise is reduced as well. There's one more neat trick we do in the resolve is that we actually process 4 pixels at the same time. This increases some of the VGPR pressure on the shader, but it reduces the memory bandwidth considerably. So suppose that we're only using one ray to resolve the 4 pixels. We only need to fetch the intersection coordinates of the ray just once for the 4 pixels. And while the intersection coordinates will be the same, so we would sample from the same location in the color buffer, it actually ends up that because of the prefiltering we use, the MIP level will depend on the roughness, because if you remember the cone, its extent will be different depending on the roughness. So we would still need to take 4 taps from the texture, and then still do all of the cone. We will need to take still 4 samples from the texture and not benefit much from the 4 sample resolve. So we use a trick which is similar to the DXT texture compressions. We find the min and max MIP level for the sample and we just interpolate the results. This means we only had take 2 instead of 4. And here's the comparison. We have the first image with just 4 text fetches, and the second one uses the interpolation, and they're pretty much the same. Whereas if we try to get away with just 1, we get a blurry result. Here's a quick note about performance. So this is captured in a Frostbite testbed running on PS4 at 900p in a scene where pretty much everything is actually using SSR, even the back wall. So in here we're using bias of 0.7. As you can see, with just 1 ray trace per pixel and 4 samples used for the resolve, which is the default setting we use on consoles, we get around 2.2 milliseconds for the trace. And if we were not to use the resolve and actually trace 4 rays per every half resolution pixel, we actually get 4.4 milliseconds. And then we also wouldn't get the gap fixing. So we are able to resolve it for the resolution, and the ray reuse scheme is quite effective. And here's a video as well, I think. If I can find the desktop somehow. That's right. Okay, so here's everyone's favorite sponsor scene with some quite glossy rough reflections. This was to demonstrate the lack of errors in temporal reprojection in particular. We actually use neighborhood clamping, which is similar to the TAA algorithm as presented by Brian Harris to help in the reprojection pass here. Here's an example which actually demonstrates this occlusion you can get with SSR, and this highlights the importance of having a fallback. But if you have an SSR algorithm which is close to physically based shading, then your fallback will blend more seamlessly with SSR. So it's actually quite important to have the elongation and everything else. And you can see that the normals are preserved and the roughness and some mixture of different surfaces here. And the car scene again, just to show you that it actually works in movement as well. And the same thing with just SSR. If you look closer, you can find some artifacts, but in general, it actually works quite well. And one where I went a bit overboard and actually played with the depth of field as well, because why not? look at the gold material in particular, it's quite interesting. We can get multiple interreflections in it, increasing the saturation of the look of it, and then greatly increasing the realism. Okay, that's the video. So as a conclusion, all the requirements I set out in the start have been fulfilled. So we get the elongation, physical correctness, we get the per pixel normal and roughness variation. Not everything is beautiful though. Sometimes we can still get a very bright pixel, which is difficult to integrate against. And this still results in noise in the picture. So maybe there's something you can come up with, some kind of crazy scheme which maybe would detect them, kind of like in the sprite depth of field, and sample them more. Maybe you could use adaptive multiple importance sampling to bias the rays towards the direction of the brightest spots. Maybe you could track the variance of the integrand and just blur the image more. So that's basically it. Thank you for listening. We actually, I think, have some time for questions, which is quite amazing because I was always overrunning the time when practicing. And by the way, we are also hiring for Frostbite, so if you're interested, just give me a shout. Thanks.
Please come to the microphone for questions.
Hi, this is beautiful work. Thank you for the presentation.
Thank you.
Could you talk about the trade-offs you're making between the quality and performance when you do linear marching?
When we do, sorry, what?
When you do the linear stepping.
The linear stepping. We basically have a fade-off, like a smooth fade-off between min and max roughness value. You can tune it. In fact, the high-precision ray tracing will generally be much more precise and result in fewer artifacts. But if you don't have complex visibility, for example, like tables everywhere with very thin depths to them, then the linear marcher will give you pretty good results anyway.
Right. So how many samples would you be taking on average?
Many samples in the linear marcher currently?
Yeah.
I think we use 32.
42. Okay. Okay. And what about the quad tree? When you build a quad tree, you have to make a decision about how deep you want it to be.
It's basically is a full map chain, which is the calculation you might already be doing if you're using tiled lighting, because then you'll be calculating min and max extents. So you can reuse the same shader to actually output a full map pyramid of the depth, and then do maybe a last fix a pass because
so how many levels would the tree have on average?
The full map chain, so depends on your resolution.
So all the way to 1 by 1. Okay.
Yeah.
Okay. Thank you.
Thanks for your talk. I remember the Yasin's paper from GPU Pro 5, and actually with his high-Z SSR with the quad trees, he was claiming to have contact hardening SSR as well for varying roughness surfaces. So what was exactly wrong with his approach? Why you couldn't just stick to that technique?
Difficult to eliminate artifacts, actually. Yasin's approach pretends to be a cone tracing algorithm, which needs visibility for each of the cells. So the way it works is actually it traces towards the first intersection point and then accumulates the samples there. But then it tries to proceed further. And for that, you actually need to trace behind surfaces, which is impossible if you don't have depth billing. And then if you have like a constant depth assumption for that, then you have to pretend that each cell has, for example, 10% visibility. And what this will end up doing is actually tracing behind walls. So in many cases, it looks fine, but when you have a complex scene, you can actually sometimes get very bad artifacts. So that was very difficult to solve, and that's why we actually have, for now at least, abandoned that algorithm.
Thanks.
Okay.
Well, let's thank the speaker for an excellent talk.